Hello, this is Mike Bradley, Marketing Manager for the FTIR products at Thermo Fisher Scientific. Welcome to the first of our short presentations about Fourier transform infrared spectroscopy. This one will cover what is FTIR, just the very basics. Later talks will cover the function of the FTIR and a lot about sampling and the use of the instrument. Let's just jump right in. The letters FTIR refer to Fourier transform infrared. The first part, the Fourier transform, refers to a mathematical function used to convert data from one format, time domain, to another, frequency domain. The second part, IR, refers to the type of spectroscopy, the infrared, which involves the vibrations of molecules. This type of unit, the FTIR, has been the most common type of infrared spectrometer since about the mid-1980s. This is in large part due to the development of the computer. Shown here first is a unit from the 1980s. This is a Nicolay 7199, and you see at that time it filled most of a room. A more modern unit, here shown the Thermo Scientific Nicolay IS5 FTIR, is a very small unit, can be easily lifted, and is run off of a simple little laptop computer. So the total amount of space has gone way down, the size of the instrument's gone way down, and yet there has been an increase in the capabilities of the instruments as these changes have happened. The mathematics grew out of work by Joseph Fourier, who actually accompanied Napoleon Bonaparte. It's the theory of heat flows where he started, and he developed the Fourier series. The Fourier transform, a little more developed version of this, just converts a function of time into a function of frequency, which is what we're going to be working with. As a highly simplified explanation of the Fourier transform, let's consider Beethoven's Ninth, shown here, highly simplified, just the melody. Compress this all down into a single pulse such that every note you saw on that upper lines are now compressed and played all at once. If we then applied the Fourier transform to it, this would report on how many times each note was played, or the intensity at each frequency. Shown here first is a bar graph. You see that there are 7 of the C's, 7 of the D's, 10 of the E's, 4 and 4 each of the F's and G's. Now, if we just show this in a slightly different form, here we see it as basically a single beam, or a spectrum, so to speak, of the different things where you have intensity versus frequency. The second part of the phrase, IR, stands for infrared spectroscopy. Basically, light interacts with molecules. In molecular spectroscopy, you have a study of the interaction of that light with molecules and the subsequent extraction of information from that data. That's the critical part. We're going to be able to convert that spectral information into information about the structure of the molecules. And here is how that relates. The absorption of the infrared light occurs at a specific frequency. Imagine those piano keys, each playing a single frequency. When the molecule absorbs, it absorbs at well-defined frequencies. And those frequencies are determined by the mass of the atoms, the strength of the bonds, and the environment around the molecule. In short, the frequency is proportional to the square root of the strength of the bond, K, divided by what's called the reduced mass, mu. So as the mass goes up, the frequency goes down. As the spring constant goes up, the strength of the bond, in other words, increases, the frequency would go up. Now there are a couple of rules about what kind of bonds will absorb infrared radiation. One of the most important is that the bond, as it vibrates, must undergo a change in dipole moment. Basically, this means that the two parts of the molecule, the two ends of the molecule involved in the vibration, must be different somehow. So you've got here a chlorine on one end, a hydrogen on the other. If you have a nitrogen on both sides, N and N, those two ends are identical. That molecule does not have a dipole, and it will not absorb infrared radiation. This is why it works as an excellent gas to purge out the spectrometer. There are other rules, such as the alignment with the electric field, but this is the main one. The molecule must change dipole moment, and if it does, we get an infrared absorption. Now let's see how the concept of Fourier transform and the absorption idea combine to give us a spectrum. Let's go back to Beethoven's Pulse, that from the Beethoven's Ninth here, and there's that single beam again, and we're going to call that I0. That's the initial intensity. Now, just for fun, let's assume that we have a filter somewhere that absorbs 5 units of the E note. If we plot then what it looks like, here we see the plot once the 5 notes are absorbed. Now, this information, all the information we want is there, but the presentation is a little convoluted because it has the original signal and the absorbed signal all put together. In order to make it clearer, what we're going to do is ratio these two, I divided by I0. We'll multiply that by 100%, and this is called the percent T, or the percent that's been transmitted. Since the C, D, F, and G, all 4 have the same intensity after as they did before, when you divide, you get 1, you get 100% in this trace. However, for the E, half of it was absorbed, you get a 50%, and if we plot it, it looks like this with a dip in the middle. That is the spectrum of the filter. That's the spectrum of the filter that absorbed the light. As you would expect, the situation in molecules is a little more complex. This is ethyl acetate. On the left, you see the stretching motion of the molecule, which is vibrating those carbon-hydrogen bonds. Now, hydrogen's light, therefore it has a low mu, or mass. And as the mass is low, you remember from the equation, that makes the frequency, or in this case the wave number, relatively high, around 3,000. A deformation moves bigger chunks of the molecule, so there's more atoms moving, it's a little heavier, and it's also easier to deform a spring than it is to stretch it, so that the K, or the spring constant, is also lower. These combine to lower the frequency for the deformation well down, and you see it's around 1,000 or 1,200 wave numbers. So this is the idea. Depending upon the Ks and the Mus, you get peaks at different regions. These give us information about the structure, and by learning about that information and by categorizing it or putting it in libraries, we can now begin to extract the molecular information that we're seeking. So that concludes our simple look at what is FTIR. There are many more presentations available which will tell you more details about how the FTIR works, why you'd use FTIR, and then some longer presentations looking at sampling, and then many more application-specific webinars and other content that is available to you. We hope that you come back and view that material. Thank you for listening, and have a great day.